properties are the point functions. You can see here, when the system is reaching from state 1 to state 2, no doubt the areas are different here. But if we consider the change in volume during this process A, the change in volume during process B, the change in volume during process C are same. If we follow process A, volume change is 3 meter cube only, that is V2. So before that, let me explain here. These properties, they have exact differentials and they are designated by the symbol D. You can see here, for this process, a small change in volume during the process is represented by dV. This change in volume, and the total volume change during a process between states 1 and 2, it is represented by the symbol integration of 1 is to 2 dV. So this dV means it is nothing but V2 minus V1, or we can call it as delta V also. All the meanings are same here. And this volume change during the different processes are same regardless of the path followed. You can see here, if I follow this path, the change in volume is same only, that is 5 meter cube final volume minus initial volume, it is 3 meter cube only. If I will follow this path, the change in volume is same. If I will follow path C, here also the change in volume is same. You can see here, for process A, process B and process C, the change in volume is same for different processes regardless of the path it has followed. Hence, we are calling it as, these are nothing but the point functions. These are mainly dependent on the end states. They are not dependent on which path it is following. That only I have given you example. If we follow this path also, the volume change is same. If I follow this path also, volume change is same. If I follow this path also, volume change is same here. For that purpose, we call that these properties are the point functions, because they are mainly dependent on the end states and not on the path which is followed during a process. So now let us study next, what do you mean by moving boundary work or PDV work. Now let us consider a gas which is enclosed in a piston and the cylinder arrangement. So this is my cylinder. So this is the piston in which the gas is enclosed in a piston cylinder device. Let P be the initial pressure of the gas and V be the volume of the gas, and where A is the cross sectional area of the piston. Now if the piston is allowed to move through a distance ds in a quasi equilibrium manner, in a very slow process, in a slow manner, then the work done during this process, how we are going to write? Delta W is equals to F into ds, force into distance. So already we know that pressure is given by the formula P is equals to force per unit area. So therefore F is equals to P into A. So therefore this F is replaced by pressure into area into ds, it remains as it is. So cross sectional area of the piston, so this area into this length, that is, it is nothing but dV, that is change in volume. You can see here, this length into this cross sectional area. So I can replace this A into ds by dV. So this expression, so how I will write now? Delta W is equals to P into dV. So this expression explains us why the moving boundary work, it is called as the P into dV work. Now you can see here, the total boundary work during the entire process as the piston moves from state 1 to state 2, it is obtained by adding all the differential works. So how I will write the total work done? W is equals to integration of 1 is to 2. It indicates from state 1 to state 2 the piston is moving. So it is given by P into dV. So you can see here, so this is pressure and this is volume. So this is the system is changing from state 1 to state 2. So this is my process path. So here I have considered the change in volume dV here. So definitely if I will consider this change in volume during this process is the dV, and I will consider this as the area. So since the area under each curve, it represents the work done. So I will consider this area, small area, as the dA. So dA, how it is given? P into dV, because area under each curve, it represents the work done. Work done, how we are going to represent it? By P into dV only here. You can see here the piston is moving from this position to this position. This sketch only here it is. See, on this diagram, the differential area dA is equals to P into dV, which is the differential work here it is. So if I want to write, this is the differential work, if I write only P into dV. So the total area, if I want for this entire area, how we will write? For process curve 1:2, by adding all these differential areas. That is, area A is equals to integration of 1:2 dA is nothing but integration of 1:2 P into dV. So already we know that since this entire area, it represents the work done during this process. So area A, if I want to calculate this entire area A, how will I represent this? Integration of 1:2 dA, differential area. That means I am going to add all these differential areas. Then it indicates total area. So this I can represent it by this symbol. 1:2 dA is nothing but P into dV, which is the differential work here.